Yes, so can you see the screen?
Yes, sir.
Okay, so first of all, this will be very informal lecture today because we will discuss some problems. And of course, if you have any doubt, then we will discuss that. So first of all, we will start with deformation retract. So what are the geometric meaning of that? So we know what is the formula and what is the procedure, right? And we know this is just a map. And but what does it looks like in geometry? So first of all, if we take say cylinder, okay. So cylinder means actually it is a say some S1 cross some 0, 1. You can think like that. Or here we may write it is minus 1, 1 as well. That does not matter. Now, can you tell me, so what will be the cylinder deformation retract to a space? Can you give me a space? Yeah, you can unmute. You can unmute. You can talk because that is just a problem session kind of thing.
So circle.
Right. So we can have a deformation retract to circle. So now can you give me a precise map? So a R from that X to A, right? That it retraction. So can you give me that if X cross I to X cross I? Sorry, X cross I to X. X cross I to X, where we can take that retraction is also a map from X to X. Now, can you define such a map? So how it is a retraction? So this is my cylinder.
So we can define by convex path.
Right, but how? So in this case, we can consider this cylinder as say S1 plus 0, 1 as well, right? So that is fine. Now, how you will make a deformation retract to a circle? Now, what will be your circle first of all? Which circle you want to deformation retract to this of this space to a circle? So can you give me a circle first? And then you can define this map.
Circle at 0, comma 0 with radius 1.
Right. So do you want mean that this circle, right? If I take this one, S1 cross 0, 1, that's mean this is just a S1 cross 0. Right. Now you want to make a deformation retract of this space. So how you will make a deformation retract? So this to this.
Like if we take an arbitrary point as x comma y comma z, if we consider it as embedded in R cube,
Mm-hmm.
then we can make a we can make a deformation retraction as f of x y z t equals equals 1 minus t uh, x y z plus t x y 0.
Right. So
So
that
basically
is
x comma y comma 1 minus t z.
right, right. So that's mean you can deform in this way, right? So that is the main purpose. So at 0 stage, say everything will be the say identity, and at 1 stage, when t equal to 1, then everything will to this one only. So you can define in this way, say your x, y, z in x. X means my S1 cross 01. Right. So, or you can, if you want, you can take that x equal to say cos 2 pi, say 2 pi x, or instead of y you can write cos say 2 sine 2 pi n. That 2 pi y. That is also fine. But if we take in this way, then we can define f of this x, y, z, say t, in this way that okay, I should not write. Shall I write in this way? There too much bracket is there. Oh, sorry. Right. So this can be your deformation retract. Right. So that's mean whenever you have this point, so at t equal to 1, that will be my x cross y cross z, right, in the cylinder. And when t equal to 1, that point will be projected to that point. Right. Similarly, if you have this point, then it is gradually coming to this, and it will move to this direction. Right. In this way, it is coming. And also, if you have say some point this one, which is already that z axis is 0, that is some x comma y comma 0, right? Then it will be fixed throughout all the t, because your z equal to 0. So therefore, this is always fixed for any t. In this way, you are deforming. So that's when deformation retract means it is just this topological space, and you are just pushing this in this direction, and right, and this gradually, and gradually this space deformed to this red circle. Right, this is the topological meaning of deformation retraction. So you can say that deformation retraction of the cylinder is this circle. Now this is one way. Now there is another way to give this deformation retract. So you do not need to take, so there is no specific thing here of this circle. So you can change the circle as well. So instead of this boundary circle, you can take circle in the middle as well, or in any place. For an example, now suppose you take your cylinder in this way. Say S1, say cross minus 1 comma 1. And say this, and this circle is your S1 cross minus 1. Say this one is S1 cross 1, right? And say you have that middle circle. Now this is S1 cross 0, right? Now similarly, you can make a deformation retract to this one in this direction, and this from this direction. That's when at time t both are fixed, and at say t equal to half, this circle comes to this one, this place, and this circle come to this place, and gradually it retract to this one. Right? Similarly, we can define map as well. Right? In fact, you can give same map, I think. Right. Here also you can give the same map. So f of say x cross y cross z comma t equal to, you can take x cross y cross 1 minus t comma z. Right here your z is negative and positive both. So therefore if you take t equal to say 0, then everything is same, that is the identity. If t equal to 1, then that part will be 0, right? And if your t increases from 0 to 1, then your z is decreases. So it is comes from this direction and it comes from this direction. Is that fine? So that's mean cylinder is a deformation retract to a circle, and we can take any circle here. In fact, here you can take, it is not specifically this middle or this one. You can take some kind of this kind of circle as well. But it is difficult to find that exact map, but we can find actually. If you want, you can also find that map so that it is moving in this direction. And that will be deformation retract to that circle, right? So that is enough. So that's mean there is no specific thing of that boundary circle. Now suppose you have some open cylinder. Open cylinder means it is S1 cross 0, 1. It is a cylinder. This circle and this circle are not included. Okay. Now, can you tell me what will be the deformation retract of this open cylinder?
Circle.
Circle. So which circle? Can we take that boundary circle?
Yes, sir.
But boundary circle is not a subspace of that one.
It's just open cylinder.
So S1 cross 0 is not a subset of this your X. So how can you choose? With your A is need subset of subspace of X, right?
We can take like S1 cross half.
Right. So we cannot take the boundary circle. We cannot take boundary circle. Instead of boundary circle, we can take any other circle. So we can take not only half, you can take this say S1 cross 1 by 3 as well.
So will its edges boundary circle will behave like open set that its boundary will not be in the cylinder.
Right. So that's when we have taken S1 cross open interval 0, 1.
Oh, that.
Okay. So that's mean that S1 cross 0 is not included and S1 cross 1 is not included, but other part is included. So whenever you have this open kind of thing, say this kind of open topological space, then you cannot take that boundary. It does not have actually a boundary. So you cannot take boundary 1. So you have to take that inside any circle. So you have to understand that, right? That is a trivial because this is not included. Okay. So if you have
Yes,
say
sir.
closed cylinder, you can take this lower boundary or upper boundary and you can either uh, push from upward or push from backward. That is fine. You can take middle circle. In that case, you can push from upward and push from downward together. That is also fine. You can take this kind of slant circle. This is also fine. But if you have open, anything is fine other than that boundary one, because boundary one is not a subspace of that. So we cannot take consider that. Other one is fine. That is trivial, right? Okay. Now suppose you have Mobius strip. You know what is a Mobius strip, right? So Mobius strip means this and this. And then, so what do you mean by this and this? That's mean, so all of these points of this one identified would be identified with all of these points of this one. So that's mean this point will be identified with this point. Now this point will be identified with this point in this way, right? So we get a Mobius strip. Now tell me, what will be the deformation retract of the Mobius strip?
Circle.
Circle. Now can you give me the circle?
Yes, sir. If you the middle points are mapped to same points, so we get a circle there.
Okay. So you are saying that if we take this point, we will be identified with this point. So you take this circle, right?
Yes, sir.
Okay. So can you take any other circle?
No, sir.
That is actually possible. You can take another circle. So can you now
But
guess
like
that
that
circle?
circle has to go twice, right? Once, like it has,
No. As
uh,
I told you, just think about that.
like it will go on both sides of that rectangle. No,
No,
that.
no, no. That will
Uh,
not be deformation retract. But think
uh,
about that. So that there is another circle. There are another two circles actually.
Diagonal.
Right. Diagonals. So diagonals also will work. So you can take this. We know that this point is identified with these points. So you can take this one as well.
like when we say this diagonal is going on both sides of the sheet.
No, no, no. You can see
Uh,
this point is identified with this, right? So this point will be
uh-huh.
identified with this, and this point will be identified with this one.
Right.
So the
Uh,
diagonal will be one circle.
but on that folded, like when you showed the folded sheet, like after identifying the points together, then how does this diagonal look?
So your this diagonal will look like this. It will go from this one,
Hmm.
and it will come this one only.
Okay, okay, okay.
Okay. Anyway, so now think about that. It
And
is
the
fine.
middle blue line, if you would have taken the middle blue line,
Yeah,
that
it
will
will be goes to
that will
the
make two
middle.
rounds
No, no, no,
on.
not two round. It is go in this way.
Acha, okay, okay.
Because if you take two round, that is not a circle one. That is not a deformation retract. Okay. Now if you have this deformation retract and this deformation one, now you know that this is a deformation retract. Now can you define a map for this one? Why this is a deformation retract? Because this is not just a sheet, right? We have some identification on the sheet as well. Now if you take the deformation retract, now why that continuity will stay?
Sir, question map is continuous.
Yeah, that is fine. But what will be that? Okay, give me. Can you give me the deformation retraction?
The same map will work. X, Y,
Yeah, the
T.
same one, because you can deform in from this direction and from there to there. That's mean here you better to take instead of you can take say um, 0 say 2 cross say minus 1 comma 1. You can take in this way. You can take this Mobius strip in this way, and then you identify and show that you can define that map. So f of x cross y cross z comma t equal to f of x comma y comma 1 minus t in this way. Why this is? See, now note that here when we are deforming in this way, see this point. Now we know that this point is same as this point, right? Now this is going in this direction, right? And see, and this is also going in this direction. So that's mean that continuity stays. Did you get what I'm saying? See, this point, these points is actually my this point. Both are same points. And this red point are same points, right? So this one actually, so if you take this direction, this line segment, now this line segment is same as this line segment from this to these directions. So if I give from A to B, then that will be my A to B. So this AB edge is same as this AB edge. So therefore, if we take that deformation retract, that is from upper to lower, and here it is lower to upper. So that's mean it is continuity stays. Right? So we are not breaking the continuity. So that is the reason. So this will be a deformation retract.
Sir, it is two dimension x, y, not x, y cross z.
Sorry. I mean, I just mean in this way. It is not even this will not even work. Right. Because it is not even in the 3 dimension after identifying. It is going to the 4 dimension. Right. We cannot give a precise map there, but you can say, so what is this? Because then if you apply in this direction, then in the quotient map it will be, that's mean if you take this deformation retraction of this topological space, then under that quotient map, since quotient map is continuous, so you will get a deformation retraction of this topological space to the boundaries to the circle. Okay. So that's mean here you take that boundary, that deformation retract x cross y comma t equal to say x cross 1 minus t comma y. This deformation you can take, and then you can take that image of this map because you have a quotient map and that is a surjective. Okay,
Yes, sir.
fine. Now, right. Now suppose you have, so this annulus you have. Annulus means this one. And you have that cylinder. Do you know that annulus and this cylinder both are actually homeomorphic? Can you see that?
Yes, like if you expand, like if you try to deform the cylinders so that you push the top downwards and expand the sides, you
Right.
will.
So it is just a deformation, right? It is not a deformation retract. It is just a deformation. So that's when you can expand this one, then that circle will be bigger and bigger, and then you can just pull that is little bit push it there, and then you have get this. You can get this figure, right? So both are homeomorphic. You can see that. You have to just stretch that upper part, and then you can make it flat. So that is enough, right? So again, now if you have this one, say this kind of annulus. Now suppose you have Right. Now, if you have this annulus, you know that that annulus is a annulus deformation retract to a circle, right? And in that case, we can take either that inside circle or the outside circle. Similar as we have taken this circle or this circle. Now, suppose you have an open annulus. That's mean you have this and this. That's mean it is something kind of x square plus y square. Say 1 strictly less than this. You have this kind of annulus. Now, can you what will be the that is that that open annulus where it will deformation retract to which topological space?
S1.
S1 again. Now can you give me that S1 which circle at which circle it will be deformation retract?
Any circle in the interior, like not in the
Ex
boundary. But
exactly. So we can take any interior one, right? So this. Now we will use actually so this kind of concept we will use this kind of concept in that Van Kampen theorem. So when we compute that fundamental group of many topological spaces, right, by using that Van Kampen theorem. Okay, so now just I state what is the Van Kampen theorem. We in the last lecture we proved that EG version of that one, and similarly one can prove that main version. Also, I skip one part that is the difficult part here also, but you can just it is well understood why that map is actually the kernel. That collection is the kernel, right? That is almost one can visualize. Okay, now this is the statement. Now it says that so let X be a topological space which is union of, remember that open, this is important, open path connected subspaces. That's mean you can take X equal to union any arbitrary collection A alpha where this A alpha are open and path connected. Okay, this. Now also given that A alpha intersection A beta and A alpha intersection A beta intersection A gamma are path connected for any alpha beta gamma in this index set. That's when you have a arbitrary collections of open connected subspaces such that X is union of that, and if it is given that their pairwise intersection, if that is non-empty, it is not necessary that it is empty. It is if right now we have taken that is non-empty exactly. So R non-empty and path connected. Otherwise also it is not. Otherwise also it is possible. Shall I include that or not? I think Hatcher did not include that. Others also one can prove that. Okay, we for a time we do not need that non-empty. That is fine actually because of that path connectedness. Okay, just we assume that if they are non-empty, then they are path connected. That can be empty as well because that is also fine. Okay. So for any pair and for any triple, it is path connected. Their intersection is path connected. Now then, pi1 x. Now I am not writing that point, right? Because we do not know where that point will be. Because if we assume that all are non-empty, then we can choose that x0 from the common intersection. Okay, so that is isomorphic to that product of that free product of pi1a quotient with n. Now what is n? Now where n is the normal subgroup generated by this one. So omega some alpha, so w some beta inverse, where this w belongs to pi 1 a alpha intersection a beta. Now this is for all alpha beta belongs to this that index set, this one. Okay, so this is the statement of Van Kampen theorem. So suppose you have a topological space X and you want to compute its fundamental group. Now what you can do? You can first divide this X into union of open path connected topological spaces so that their fundamental group is easy to compute. Now if you can do that, then pi1 of X will be, that is isomorphic to free product of these groups quotient with n, and n is the normal subgroup generated by this. Okay, so we prove this when X is a union of two open path connected topological space, but it is true for the arbitrary as well. Right. Now by using Van Kampen theorem, now quickly can you give me a fundamental group Sn? Okay. First of all, fundamental group of S2. Can you give me that? What is the fundamental group of S2? So we have proved that that is empty, right? So there is a proof. So I just that is proof I have written in the lecture note, but I did not explain the whole proof because I asked and you said that there is no doubt. Okay. Now, can you give me, by using that Van Kampen theorem, can you give me the fundamental group of pi1 of S1, that is 0? Can you prove that? Yes, that is easy actually. Just see the statement and tell me. Miss anyone? You don't know that? You should know because there will be many questions from the Van Kampen. You should understand. So what we need? What we need to just take that S2 into union of open path connected topological spaces. So what kind of topological space we can take?
It's a two half of the sphere, upper half and lower half.
Right, but if you take upper half, that is open upper half or closed upper half?
We should make open set A and B.
But if you take open upper half and if you take that lower closed open upper half,
Yes,
but
yes.
then their union will not be S2, right?
Yeah, we can take like something larger than upper and lower half so that they intersect and their
E-
union is
Exactly, exactly. So
not.
what we can take? We can take, say this is my sphere. So we can take this one. So this one and then this one. Right? That part. And we can take another one this, and we can take this part. right? And if you need any easiest example, you can take u equal to Sn minus that one point. So this is my n, this is my s. You can take that one as well. This is also open. And you can take v equal to say s2 minus that point s as well. Now both are open. And what is u intersection v? That is s2 minus n comma s. And that is deformation retract to again circle. And here also, if you take say this is my u and say this is my v, then also u intersection v deformation retract to circle, right? Now what is my, now we know that anyway, so we know that Sn S2 minus n, that singleton point n, that is homeomorphic to R2. We have proved that. So therefore pi1 of S2 minus n, what is that? That will be 0. Now pi1 of S1 minus s, that is homeomorphic to R2, that is also 0. So therefore by Van Kampen theorem, we have that fundamental group is pi1 of x is pi1 of u star pi1 of v quotient with n. But here it is 0 star 0 quotient with n. But that does not matter because that is 0. So that is 0. So you have fundamental group of S2 equal to 0. That's all. Okay, is it understood?
Yes, sir.
Okay. Now there is another
एन वाला
notation.
फिर से बता दीजिए.
Huh? What? Which one? कौन सा? Hello?
How to choose n?
Which end? This one?
Yes, sir.
Oh, this one just north one, North Pole, and this is just the South Pole. So we know that stereographic projection, right? And we can project through n, and we can also project through s. That is called a stereographic projection in n actually. So if you take that one, that's mean by this one you can take Sn minus this is homeomorphic to R2 actually. So in fact you can take Sn minus n, that is homeomorphic to Rn. And what is your n? N is your 0, 0, 0, comma 1. And what s is 0, 0, everything 0 is minus 1. These 2 points. And this homeomorphism is called just a stereographic projection. Okay.
Yes, sir.
Right. So another one is called a Weiss product. So it is written as S1, this symbol and S1. So this is called a Weiss product, and that's mean it is a, this one a circle, and you have another circle, and just a, they share a common point. Okay. So that's similarly if you have say S2 Weiss with S1, so that's mean you have a sphere and you have a circle, say this one. So they shares a common vertex. Okay. Now we can, now by using Van Kampen theorem, it is easy to compute the fundamental group of these topological spaces. Now we compute fundamental group of this first of all S1 with S1. So what is that? Now this is my one circle. This is my one circle. Now I ask you, now you have to give the answer. Now for this, can you give me U and V? So it is embedded in R2. Okay. Now can you give me one U and one V? for this one? That is
Yeah,
simple.
we can take U to be S1 and then a bit of extension with the V shape.
Exactly. So we can take my open
Like a
set in
tie
this.
shoelace kind of a thing.
Yeah. So we can take my open set this one U in R2 and then we'll take intersection and we can take this one. This is my V. Okay, in R2. Now what will be the open set in S1? So say U dash, that is my main open set. That one will be this form. So I can write in terms of green. So this circle, okay, along with this portion. Okay, and what will be my V dash? V dash will be this way. So there are something in topology in business more in the algebraic topology. So it is sometimes it is difficult to write in terms of formula. Okay, so it is fine. So the main idea is you understand or not. It is fine. You can explain that in terms of picture. Okay, so you can write. So your open set is this one, and your V dash is this one. But whenever you write a picture, you should also write little bit very carefully so that it is well understood. Okay, so that's when this is okay. So this is your U, this is your V. So that is your open set U dash and V dash in S1 with S1, and here U comma V open in R2. Okay, so we have taken those open sets intersect with that this one. So the open sets in S with S1 with S1, that will be this and this. Now what will be S1, sorry, what will be then U1 union, sorry, U1 union V1, that will be your the whole space, and what will be that intersection. So we can say U dash intersection V dash. Now what will be that intersection looks like? That will be kind of this and this. Is that clear to everyone?
Yes, sir.
Right. Now can you tell me what is the fundamental group of U dash, V dash and their intersection, and why? Yes, tell me. What is the fundamental group of U dash? What is the fundamental group of V dash? And what is the fundamental group of U dash intersection V dash? What are those?
Sir, I think
U dash will deformation retract to S1.
Right. And this
yes,
one and their intersection?
U dash and V dash will deformation retract to S1, and the intersection, I think we can retract it to that intersection point.
Right. So this is deformation retract to S1. So that is fundamental group of U dash equal to, you can write it is Z, and we can write it is generated by alpha. Okay. And V dash deformation retracts to again S1. Now that is pi 1 v dash equal to again z, and but we need to take a different group, right? Because of that star, that is free product, we can take say beta. And u dash intersection v dash deformation retract to a point. So that is pi 1 u dash intersection v dash, that is 0. Right now, by using, just use the Van Kampen theorem. Then by Van Kampen theorem, what is my phi 1 x? Now tell me, what is that?
Z cross Z.
No. Any other answer? Yes. This is our version only, which we proved. Question to it n, but that is 0, and that is alpha star beta. So that is the fundamental group. So that is Z
Star Z.
star Z. That is free group,
Sir, n is equal to 0. How we?
because that is a point, single point is 0. What
Sir,
is
No,
n?
but like, n is generated by W alpha W beta inverse, where W
Belongs to what is n?
U1 intersection V1. But
What is n? N is generated by W, say here alpha
so in uh, yeah, so like
beta,
U1
sorry,
intersection V1, that is 0. But if you take W alpha, that may not be always the same, right?
why?
uh, because like in the homotopy classes in U intersection V and the homotopy classes in U, they may not be the same. Uh,
No, but your this group is 0. So therefore you can take W equal to always. W is just a representative, right? So you can take that W equal to your EX0, that point only. It is not moving anywhere. You can take W is a path equal to x0 for all x, for all s. Because there this group is 0, right? So your domain is 0. So your that's for code that image should be 0.
Sir, can you explain the first part how U dash deformation retracts to circle?
So this one,
Yes, sir.
yeah, you have a circle and you have some part of that this way. So what you can do, you can deform this portion. That is, this is kind of one edge, right? Now this is deformed to this point. Now this is deformed to this point in this direction.
Not understood.
So this is a circle and this is a curve segment, right? If you take any curve segment, this one, now that is deformation retract to this point on, right? Any line segment, if you take any line segment, that is deformation retract to a single point, right?
Yes, sir.
So in this way, that curve segment, that is deformation retract to single point, and this is also a curve segment. So this is deformation retract to this point. So this is deformation retract to these circles only. And similarly, this one deformation retract to only this circle, because that portion will be deformation retract to a single point. And similarly here, what is that? That is a X kind of thing, right? This kind of thing. So therefore each of the line segment, it is union of 4 line segment and starting at one point. Now we know that any line segment is deformation retract to a point. How to prove that 0, 1 is deformation retract to a singleton 0? You can just take x going to, that is f of x comma t. You can take tx. This is your x, this is your a, and this is your map x cross I to x. Or you can take 1 minus t comma x. So that at 0 it is identity, at 1 it is just a point 0. Is it not clear?
It's clear now, but I don't understood what do we mean by S dash V S dash?
Which one?
Like U dash union V dash equal to S dash V S dash.
No, no. See, what is a open set? Who is asking this question?
Asutosh.
Ashutosh. So you have done topology course, right? Now you have a topological space X and you have a topological space Y subset of X. Now what are the open set in Y? What are the open sets in Y? The open sets is any set open in Y means, say U is open in Y means U can be written as some V intersection Y, where V is open in X.
Yes.
So this is open in X, then only you can say that it is open in Y. Right. So we need a, so what is Van Compen theorem says? We need X can be, see, right. So X can be written as a union of open path connected subspaces. That's mean A alpha is a subspace of X and that should be open. So
Yes.
what kind of open set that will be then? Then what we'll do? We take that disk U in R2, that is open in R2, and then take intersection with whole space, that is Y. Then we get only this portion. So we get only this portion. We get only this portion and this circle by taking that intersection. And we call that is U dash. So that's mean U dash is open in S1 cross S1. So that's mean here these points will not be there. These points, those boundary points will not be there. Okay, and similarly V dash. Now by the construction you can see that U dash union V dash will be your whole topological space. This one.
Yes, sir.
Okay. Now this part is clear. Now this part is also clear. The last part. Why
So I'm
this
not
in
getting what the notation V, like we have written S dash V S dash. What is the notation? Is it cross S
where
dash
where
cross?
where? Oh, this one, that V.
Yes, sir.
No, that is just a base product. Base product means just I see I have explained here. So that's mean if you have two topological space, then base product means they have just a common point. That's all.
Okay, sir.
So
Understood.
we identify one point of one point together. So take one point from S1, take another point from S1, and we identified them. That's all. Okay, so this is this kind of thing.
Yes, sir. Thank you.
Okay, now this part is clear. Why this n is 0? See, your this topological, sorry, this fundamental group is 0. So that's mean you can take your W is always your EX0, where X0 is the base point. That's mean W equal to you can take EX0. Now if you take now W1, now that will be again EX0 only. So that's therefore if W equal to 0, so that's mean that W1 that is also 0 and W2 that is also 0. That's mean it is just the inclusion map, right? So inclusion map from pi1 this to this. Now if your this domain is 0, then codomain should be that image should be 0. So there is no meaning of this n then, right?
Yes, sir.
Okay. Now any doubt of this problem? Any other? Okay. Now we can take another topological space, say clean bottle. Now what is clean bottle? Now find a fundamental group of clean bottle. So clean bottle means this. Okay, now we identify this with we can say this with this, okay, and this with this. Okay, so that's mean what we will do, we will identify this edge with this edge, then we will have a cylinder, and then we will identify this with it twice. So therefore we get a clean bottle. Okay, so but that's mean by identifying we first get a cylinder. Okay, so this. So where we have this identification with that reverse one. So therefore, if we identify, we will get something called clean bottle. It is some kind of this. So it goes through some four-dimensional object and it is going to this. So this is another one. Okay, anyway, you don't have to go through this figure and everything. We will compute that fundamental group directly. So what is this actually? So we are identifying this with this and this with this. Okay. Now what we will do? Now see. Now if you identify this, now if this is your V, this is your V, this is your V, this is your V. All the vertices will be also identified. You can check that. If you identify this edge with this edge, then this vertex and this vertex are identified, and these are identified. Now again, if when we identify the vertical that horizontal lines, then also we will the diagonal will be identified. So ultimately four vertices will be identified. So therefore this is one circle, this is one circle, this is one circle, this is one circle. But these two circles are identified. So we call this circle by alpha, this is alpha, and say we call this is beta and this is beta. Okay. Now this is called clean bottle. Now we want to compute the fundamental group of this topological space. Now can you tell me what are the what can be the open sets of this one? So how to consider this topological space X into union of two open sets? How to take those open sets? So one way what we can do, we can take this disk. So this is a disk, interior, right? So there is no identification in the interior. So therefore we can take whole interior disk. So this is my U. Okay. Now this is open. Obviously open disk. We take open disk. And what we take? We take that blue one and then there its complement. Now call that is V. Now tell me what is the fundamental group of U and why?
0.
Yes.
Right. Why it is 0?
We can deformation retract to a single part.
Right. So U deformation retracts to a single point, to a point. Right. So therefore pi 1 of U, that is 0. Now what is V? V is the complement of that. Okay. Now U and V are both are open. Okay. Now what is V deformation retract to? See what is V? First we draw what is V. Now V this.
I think we will retract to circle.
So this where that was identified. That was identified. Now this one, see now you if you deformation retract oops, to this direction, deformation retract to this direction. Okay, so that's when you just it looks like suppose you have a say a hole somewhere and you are just stretching that hole, right? That's when you are making that hole bigger and bigger. Okay. Now, what will be the deformation retract to? Now see that two-dimensional thing will be deformation retract to the one-dimensional object this. This is alpha, this is beta. Okay, where there is no interior. There is no interior, it is just the this four edges are there and with some identification. Okay, now you have just four edges and you are identifying this alpha with this alpha, then what you will get? Now if you first identify alpha, then that is same as you can say you have a circle here and you have a circle. Now this is your alpha and this is your beta. Is that clear? Is that clear to everyone? Say something, yes or no?
Yes,
Yes,
sir.
sir.
Okay, now
No,
again,
sir. No,
what?
sir.
Why it
Sir,
is not
explain
clear?
it again.
So which part is not clear? Now give
Sir,
me.
view part.
B part. So now you have a hole and you are deformation. It is a deformation retract to this. Is it not clear? This to this. This is a deformation retract. Because these points are going to these directions.
So, but circle, this will
Huh?
this circle and that is a rectangle or square.
So what? When
How
you
can we will define map? Like by geometry
by geometry you
we are
can
not
take instead of okay if you want instead of this, you can take. So we did not say that you have to take here circle only. You can take geometric figure as well if you want. You can take this. You can take your U is this one. Take this is your U. And take this is your V. Okay. Now can you deformation retract? Now you can make a deformation retract of this blue one region to this portion.
Yes, sir.
Done. We are okay.
Yes.
So this is just a
Yes, sir.
topologically. When you are dealing with topology, then you that circle, rectangle, both are same.
So what defining a map will be a tougher task in that.
Right. So that's what I'm saying. So you don't have to define the map. That is possible. So defining map is possible, but we don't need that. We don't need to define that. You should understand the concept. Okay. So this one. Now this is deformation retract to this one. That's mean when we have only 4 edges with these identifications. Now if we identify this alpha with this alpha, then we get this figure. Now again, now beta is a circle, this beta is forms a circle here. Now again if we identify, see we will identify this edge with this one, this circle with this circle, because we need to identify. So therefore this is my vertex V, that is my alpha, and that is my beta. Okay, so this V deformation retract to where it is deformation retract to S1 waste product S1. Okay. Now tell me what is the fundamental group of V then? Yes, we just computed that one. That Z star Z, right? And say this is alpha star beta. This one.
Sir, how this identification done? Second part. Beta.
So you have now 4 edges only because this is
Yes, the
deformation
first
retract.
part is okay for alpha.
Okay. Now if you identify alpha alpha, these 2 edges, then we will get this one. Now you have 2 circle. This circle, one edge, another circle. But this is beta. This is beta. We have an identification from here onwards, right? That's when we have to identify this with this as well. Now if you identify this circle with this circle, now you can see that this alpha, this vertex also bend to a single vertex. So alpha also forms a circle, and these 2 circles from this circle.
Sir, but beta in opposite direction, beta is.
But right, but in 2 dimension it matters. But here it is in 1 dimension, so it does not matter now. It is which dimension it is.
Okay.
Right. Because whenever you have some 2 dimension, then it matters. Then how to you identify in this side or you have this direction.
Because inside points are there.
Right. But because you need some either self intersection kind of thing, right? But here it is now 1 dimension. Now that does not matter in which direction you are identifying. You can
So, but
identify in this direction or in this direction as well.
Okay, sir.
the figure is in 3 dimension now, like we have folded it.
Right.
Uh,
Figure is in 3 dimension, but your object is in 1 dimensional object. That's when you are identifying only a circle. That's all. So there is no direction. So in which direction you will identify. If you have 2 circle, If you identify they are in this direction or the reverse direction, both are same. You can take just one um, say rope, and you make one circle, another circle. Now you just try to identify them. Now you will see. You can identify in this way. You can identify in the other direction as well. You can see it does not matter. You will get the same figure. Okay, try this. Take a rope. Okay, and at the boundary you make two circle and then identify two circles in reverse,
So
in the opposite direction as well and in the reverse direction as well. In the same direction and the opposite direction both. Okay, try this. Try this. If you do try this by your hand only practically, then you will see that both are same. Okay, so that direction of beta, that does not matter. See, now beta in each direction, what you can do, you can make a twist there, right here.
the direction
Then
will
that will be
matter.
reverse.
I think.
Huh?
If we are not direction is not reversed, then it will like become a loop, uh,
What will
cylind-
become?
cylindrical sphere.
But it is one dimensional, no? There is nothing. It is only just a loop, it is just a loop. There is nothing inside of this one. You did not get what I am saying. It is just kind of this. You have this circle and you have this circle. Only this. Now what you need to identify these two. You can identify in this way or you can identify in this way as well. In both cases you will find this. What I am saying, you just take a rope, okay, and make to circle to boundary and identify them. That's all. You will find. You will get your answer.
Okay, sir.
Okay, so now this is a circle S1 with S1. So that's for we take one is alpha and another is beta. So therefore pi 1 of V will be alpha star beta. Okay, fine. Now what is my fundamental group of X? Now fundamental group of X will be pi 1 of U star pi 1 of V quotient with N. Now that is 0 and that is N. So that is alpha star beta quotient with N. Now what is N here? Now for N we need to see the inclusion maps. So what is my IA first of all? Say IA and it is U I have written, right? So what is my IU? That is U intersection V to U only. Then IU star pi 1, that is pi 1 U. Now that is 0. So that is just a 0 map. Now what is pi V? To V. Now pi V star. What is that? Is pi 1 U intersection V to pi 1 V, and that is alpha star beta. Right? Now tell me, for now we need U intersection V. Now what will be here in this case U intersection V? This. Tell me what is U intersection V here?
The disk.
Disk? It is not a disk.
Annulus. Open annulus.
Yes.
Right, it is open annulus. Now this is deformed to a circle. So therefore pi 1 u intersection v, that is what? Z. So therefore say this is generated by gamma, right? So that's mean this is your gamma in circle. Okay, so this is gamma. Now tell me what is my I star v, that gamma. Tell me. Now this one. Now this is your gamma. Gamma in U intersection v. Now what will be that image of that gamma in pi 1 v?
So
What is
alpha
that?
cross 0 or 0 cross alpha.
No, this is this circle, right? This is this circle going to this direction. Now what will be the form of gamma in terms of alpha and beta? So what is that? Yes. See the figure and tell me what will be that circle in V. Now gamma is a circle in unit V. Now what is that circle in V?
Alpha, beta, alpha inverse beta.
Exactly. Now is it clear to everyone? Now that will be
Yes.
alpha in V, beta in V, alpha bar V, beta V. So that will be this. Is that clear to everyone?
No, sir.
No? Why? But see, this is your circle. Can you see the cursor? Circle? Can you see the cursor?
Yes, sir.
So this is your circle. Now this is a circle in U intersection V. But this is in V as well, right? Because it is in the blue region as well. Now what is that circle? Now that circle is homomorphic, that is homotopic to this circle. So this and this. Now what is this? This is your alpha, this is your beta. Now this is your alpha inverse because we are going to this direction and this is called alpha. So therefore alpha inverse and then again it is beta. So therefore this circle is homotopic to alpha here to here. Alpha you can start from here is this point. So this is alpha, beta, alpha inverse, beta. So this is your region.
Start from anywhere. Like
You can start from here as well. You can start
any
from here.
vertex.
You can go from this to this first, then alpha, beta, alpha inverse, beta inverse, and then you can go back here as well.
Yes, I'm asking we can start from any vertex.
Right, you can start from any vertex. Because we know this since all of these are path connected, so it is base point independent. So that any loop, anything does not depend on the base point.
Okay.
Okay, so this is 0. So therefore, what is your W then? Then it is your, sorry. Now here we have taken pi 1 u intersection V, that is generated by gamma. then n will be generated by this, say gamma b, sorry, gamma say v, gamma a inverse generated by this one. Okay, or you can say that, say gamma v is same as gamma u. Now what is gamma u? That is 1. And what is gamma v? Gamma v is, we have seen it is alpha v, beta v, alpha bar v, beta v. That is 1. So that is your n. Okay, it is generated by this. So therefore, this is, you can write it is alpha comma beta generated by these two, and quotient to it, that is, it gives the relation, and relation is this one. So you can write this is homotopy class. So you can write it is as alpha v beta v, because fundamental group of u is 0, and the relation is this one. Beta v, that is 1. And here this is, you can write in this form as well. So alpha beta equal to beta inverse alpha. This. So
Like,
this is the
why did
fundamental.
they write gamma v equals gamma u?
Right. So what is actually it says? It says this, the quotient is generated by this one, right? Okay, I should explain that one. Right. So here quotient is generated by this one. Now this is, it is a quotient group. That's mean in this group, in the pi1x, that's mean in the pi1x, the elements of n are identity.
Okay. So when gamma v equals gamma u, that is set to identity.
Right. Now this is generated by this one. So that's mean, but we know that that is, this group is 0. So that's mean n is actually basically generated by this group. Say alpha, beta, alpha bar, beta bar. Sorry, alpha bar, beta. N is actually generated by this group. Now, so that's mean here. So right. So the elements of this one are identity only in this group, because we are taking quotient over this.
Okay.
So therefore this is equal to this, and here with, then this is called a relation now. Now this is the generator and this is the relation, because this is identity. So we can say that pi1 of x is generated by this and this, where this product will be identity, because this product is element of n.
So basically, whenever we have a normal group which is generated by some relation, then like if we quotient with that, we'll get a group which satisfies that relation.
Exactly. For an example, you have, if you quotient with g with h, now you can think in this way that it is generated by g, and some say, if your g1 say g2, now if your g1 g2 belongs to say h, that's mean this is identity. So you can say that g1 g2 equal to identity, because the elements of h is identity, because the elements of n are identity in pi1x. because we are taking the quotient. Now the elements of pi1 n is element of n is this one, and where this is 0. So element of this is only this, and we have seen this is means this. So therefore this is identity. That is the elements of pi1x.
So please repeat, tell us once again how we calculate n.
Okay, so what was n? N was generated by gamma v gamma u inverse for all gamma belongs to pi1 u intersection v, right?
Yes, sir.
Generated by, it is generated by this. Now we know that this has only single element because that is z. So this has only single element. So therefore it is, so n will be the group this gamma v, because that is identity and gamma is a single element. So n is generated by this one only. Is that clear? N is generated by this one only because that part is identity. That part is identity, and we have only one gamma in this. So n is generated by this group. Is that fine?
Yes, sir.
Now this group is actually this group. We have proved that here. Where we have proved that? Here we have seen that. So this gamma equal to gamma v is actually this one.
Yes, sir.
So therefore we are writing this.
Yes, sir.
So n equal to this one. Now what is this group? This group is generated by alpha and beta, and n is the quotient group. That's mean the elements of n are identity. So therefore we write this is group is this comma this, and this is equal to identity. So we are done. Right? So this way actually you can construct fundamental group of any topological space, any topological space. For an example, if you have this kind of topological space, say this triangle, say this is identified with this, say this is alpha, this is alpha, this is alpha. Then you can easily check that the fundamental group of this topological space will be alpha, and it will be generated by alpha cube equal to 1. It is given in the lecture note. So that's when it is actually Z3. Now if you want to construct a topological space whose fundamental group is Z4, now you can take this, identify this, this. Say this is alpha, 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 alpha. That is a rectangle. Then you can find that if this is a topological space X, then you can find that topological fundamental group of X is this one. Alpha, where alpha 4 equal to 1. So this is Z4. It is given in the now lecture note. Now you can just go through that. This is simple. It is very easy to compute this. Just follow the similar approach. Okay, so pi1 u will be 0, pi1 v will be generated by only this one. Here you will have only one circle. So then you will be done. Okay, so I am stopping here. So Monisha will come up with more examples in the next tutorial session. So when you have fixed the time of the tutorial session?